Introduction. Artificial intelligence, AI, offers huge promise for development, but digital divides in emerging markets pose real obstacles. In many low-income regions, internet connections are slow, coverage is patchy, and electricity is unreliable. For example, GSMA finds that in sub-Saharan Africa, only about 27% of people use mobile internet, and a 60% usage gap remains. Millions live within coverage, but cannot go online due to high device, data, or skill barriers. African News reports that roughly 900 million Africans still lack any internet access, and a similar number lack electricity. Meanwhile, internet data in some countries costs over 5% of a monthly income. In this context, cloud-based AI, like large chatbots, is simply out of reach for most. To serve these communities, innovators are exploring offline-first AI on low-cost devices. The idea is to bring AI services into the last mile by running smart assistants directly on cheap phones or local kiosks, and using simple channels like SMS, voice, USSD, shortcode menus, instead of video apps or the web. This approach can deliver timely advice in agriculture, health, education, and more, without needing continuous connectivity or expensive hardware. The key is tailoring AI to local needs, supporting regional languages, involving community oversight, and working through trusted partners, telcos, NGOs, governments, with pricing tuned to local incomes. This article examines those constraints and solutions, drawing on recent projects and studies. It shows how fully offline or low-tech AI assistants can be feasible and impactful for agriculture, health, and education in emerging markets, and how partnerships and community stewardship ensure they are sustainable, safe, and affordable. Barriers: connectivity, power, and cost. Connectivity gaps. Networks in many developing regions are expanding but incomplete. In sub-Saharan Africa, for example, 13% of the population still lives outside any cellular coverage, and among those covered, a 60% usage gap persists. This gap reflects unaffordable devices or data, low digital literacy, and safety concerns. Globally, about 3.1 billion people face such usage gaps. In practical terms, hundreds of millions of rural households have no reliable internet, or only 2G, 3G. As one report notes, approximately 900 million Africans, out of about 1.4 billion, have no internet, and nearly the same number have no electricity. These figures tell us that classic smartphone apps, or cloud AI, will often fail in remote villages. Power constraints. Lack of electricity further reduces digital access. In the same African News report, an expert emphasized how AI tools cannot function while continuing to work on 3G or 2G if electricity is missing. Many rural homes rely on seasonal or solar power, and charging a device is costly or unpredictable. Educational or health kiosk projects often use solar power or battery kits. What matters is maximizing usage on minimal power, for example, highly energy-efficient chips, and devices that can run for days on a single charge. Affordability hurdles. Device and data costs remain fatally high for low-income users. In sub-Saharan Africa, taxes and import duties can make even basic smartphones $50 or more, dozens of hours of wages for the poorest. GSMA notes that device affordability is a major part of the usage gap. Data prices, likewise, are a large fraction of income. A survey found mobile data costing over 5% of monthly income in many African countries, well above the UN's 2% affordability target. For farmers or students who may earn just a few dollars a day, paying even 50 cents per gigabyte is prohibitively expensive. These infrastructure and cost barriers mean that AI solutions must be radically adapted. They should work offline or on the lowest possible bandwidth, run on very cheap hardware, and consume minimal power. Offline-first AI on low-cost devices. To overcome the gaps above, new projects are deploying offline-first AI assistants on inexpensive handsets or local hubs. Advances in edge AI and model compression mean that limited AI models, e.g. for speech recognition, text advice, can now run directly on basic devices without cloud access. Some researchers propose ultra-cheap bare metal AI gadgets. Simulations show that practical language AI can run on devices costing as little as $8 to $10, with only 30 megabytes of RAM. Such models, often distilled from large systems, can answer questions or give instructions offline, storing language databases locally. In effect, they are pocket supercomputers for cities and farms with no stable internet. In practice, these devices can take the form of Feature phones with AI chips. Some startups retrofit simple phones with voice AI chips or firmware. For instance, Canada's Viamo launched an AI service in 2024 that turns any basic phone into an offline chatbot. The user dials a short code and talks or texts. All processing happens on a local server or embedded offline model. The user in turn receives answers as voice or text. This setup works even in the middle of nowhere, with no internet, only the standard mobile network signaling. It is targeted at the world's poorest, allowing queries for as little as Nen 10, about 12 cents per call. Community AI kiosks or radios. Another approach is village hubs, powered by rugged mini-computers or Raspberry Pi-type devices. For example, open-source Colibri, by Learning Equality, lets schools install a local server or Pi. Students then use any local device to see textbooks, videos, or quizzes offline. This is already in use in rural Kenya, Tanzania, and Malawi. Teachers load global educational content and adapt it into local languages on Colibri. A similar model is using Wi-Fi hotspots or local intranets with AR chat programs for farmers at community centers. Dedicated low-cost AI phones. Ambitious projects envision $10 to $20 smartphones loaded with on-device AI. One techno-economic study proposes distributing 700 million offline AI learning devices in Africa by 2030, costing $10 to $20 each. These would be preloaded with multilingual encyclopedias and interactive modules, text, image recognition, voice in multiple languages. While no consumer device is yet so cheap, the roadmap exists. Massively scaled production and ultra-lightweight models, such as Meta's Llama boosters or Metal NLLB language nets, could reach that point soon. The key across all these is low-energy, offline operation. For example, AI models can preload a subset of content, like crop databases or basic health FAQs, so that only these need to be stored locally.
And any new queries can be queued until connectivity is available.
In the meantime, the device responds instantly to the user. As technology improves, even smartphone apps are adding offline modes, allowing downloads when on Wi-Fi, then offline use. The impressive lesson is, you do not need Google or OpenAI servers if the AI model is made tiny or cached. The next move is to embed the smarts at the edges where users are. Channels and use cases: SMS, USSD, and voice. In emerging markets, the most widespread mediums are SMS, USSD, interactive text menus, and voice calls, not web apps. Any AI assistant must use those channels to reach mass users. Fortunately, both SMS and USSD are well established. GSMA reports 9 in 10 mobile money transactions in sub-Saharan Africa run over USSD, and providers globally still support USSD on all phones. Crucially, USSD and SMS require no internet data at all, just the GSM signaling channel. They work on the cheapest feature phones, even those without microSD cards or color screens. An AI assistant over USSD can send a text query like, "What pests affect maize?" 1 aphids, 2 weevil, and get a numeric reply with advice. Interactive voice response, IVR, works similarly. Users speak or listen via automated menus in local languages. Agriculture. For farmers, AI advisory via SMS voice is already happening. One example in Cameroon is the Farmer Guide app. It diagnoses crop diseases with AI, but farmers outside cities couldn't use it. They had no internet or power. The Viamo platform steps in. It offers an AI-driven service where any farmer can dial in Nigeria, Zambia, and beyond, and ask agricultural questions. The system runs on voice, SMS, and can even take voice prompts, giving replies in kind. This makes AI accessible on any phone, not just smartphones. Another initiative is Ghana's DALI AI chatbot, accessible via WhatsApp, which many African users have, or SMS. DALI provides planting advice, market prices, and weather tips. Crucially, DALI supports 27 languages, including 20 African languages like Swahili, Yoruba, Twi, etc., so farmers get advice in their mother tongue. Since 2024, DALI has reached over 110,000 farmers in Ghana and Kenya. These projects show that simple text-voice channels can deliver advanced agricultural AI to the village. Health. Mobile health mHealth has long used SMS and IVR, and AI can integrate with these. For example, Viamo's platform is partnered with UNICEF to provide offline AI chatbots for health topics, HIV prevention, malaria symptoms, sanitation tips. A user can dial a number or text a code and get instant health advice in their language. During COVID-19, many countries launched USSD tools for self-assessment and information, e.g., Sierra Leone's USSD Symptom Checker. An AI assistant can build on these by adding interactive Q&A and personalized guidance. Importantly, USSD-based telemedicine services, like Kenya's free USSD health checks, prove that these channels work at scale. Going forward, offline AI modules could run on local clinic microcomputers or even nurses' phones, offering decision support without needing online databases. Education. Distance learning in connectivity-poor areas has seen success via SMS and offline kits. Initiatives like Eneza Education in Kenya, Ghana, and Ivory Coast send quiz questions and lessons via SMS USSD on basic phones. Over 10 million learners have used Eneza's feature phone platform at low cost, proving that meaningful digital learning can happen without smartphones. Building on this, Kenya's Mshule mobile school blends SMS with AI. It personalizes lessons and feedback for primary students using machine learning behind the scenes. Teachers send quizzes to a student's phone, and Mshule tailors content based on each child's answers. Such services work offline in a sense that once the curriculum is delivered, the phone user does not need continuous net access. Communities have also set up offline educational hubs, e.g., solar-powered classrooms with local servers that use zero-rated content. During the pandemic, UNICEF and others reported that 2/3 of school children globally had no home internet, so these low-tech solutions have kept education running. Each of these use cases underscores that channels matter more than fancy UIs. In rural agriculture, health, and schooling, the simplest mobile interface, USSD text menus, or voice IVR in local languages, reaches the majority. AI attached to these channels, either on the device or a local server, can transform them from static info hotlines into interactive personal assistants. Localization, languages, data, and safety, language coverage. To be useful, assistants must speak local tongue, not just English or French. Emerging markets are highly multilingual. For example, Africa alone has over 2,000 languages. Mainstream AI models typically cover only major world languages, so tailor-made local models or translations are needed. Some promising efforts already exist. For instance, PharmaLine's DALI chatbot supports 27 languages, including 20 African languages like Akan, Hausa, Igbo, Twi, and Swahili. In Indonesia, research projects are experimenting with voice AI in farmers' mother tongues using IVR systems. An example, the International Rice Research Institute partnered with Viamo to launch an IVR hotline, providing advisory services in a local Indonesian language, so that rice farmers of all literacy levels could understand. Educational content has been localized too. The Colibri platform noted above is used in East African schools, where teachers adapt global open resources to local languages and contexts. To systematically cover local languages, projects should collect and train on regional data. One model is community crowdsourcing. Local volunteers, farmers, teachers, translators can help build glossaries or record speech samples. This data, kept locally or anonymized, can be used to fine-tune AI models to the dialects of the area. Some national efforts even produce tools. For example, Nigeria's Center for Digital Indigenous Language created a mobile AI keyboard covering nearly 180 African languages, making it easier to type and read in those languages. Partnerships with local universities or NGOs can help curate culturally correct content, e.g., local plant names, sanitary practices, so the AI advice is meaningful. Local data collection and governance. Collecting data and feedback in the field is crucial for training and improving assistance. However, this must be done ethically. Communities should consent to data use, and sensitive personal data, health records, personal finances must be protected. A useful model is community co-creation. For example, in Lagos's Makoko community, residents were trained in mapping and drone data collection. They produced their own geographic dataset, which is now used for local planning. Similarly, an AI project could equip village health workers or extension agents to gather anonymized case reports or queries. These local datasets should remain under community stewardship, stored on local servers or through trusted partners, rather than being siphoned off by distant firms. The World Economic Forum suggests training local innovators, NGOs, and agencies in AI literacy and governance, so they can choose how they tell their stories, ensuring data is used for their benefit. Local oversight committees or rural educator networks can vet the content regularly. Adjusting it for seasonal or situational changes. A community-driven feedback loop helps catch errors. If many farmers report the same problem with the AI's advice, developers can update the model. Formats should allow rapid updates too. Importantly, underserved communities should have some ownership. Deploying the technology through cooperatives or local councils, rather than imposing it top-down, ensures accountability. Experience shows that community stewardship is key. In agricultural mapping and finance, grassroots-designed tools outperform generic ones. Experts at a recent forum stressed that we must meet people where they are, with local language platforms like WhatsApp chatbots, and that tailoring AI to local realities creates sustainable gains. In practice, this means training users and leaders in each community. For example, equipping village teachers or health workers with guides on using and explaining the AI tools. Such local champions reduce mistrust and help enforce ethical norms. Collaboration and business models. Successfully scaling offline AI in emerging markets requires partnerships across sectors and pricing that the poor can afford. Mobile network operators, MNOs, telcos are natural allies. They already own the SMS, USSD, and voice infrastructure. By collaborating with AI providers, MNOs can host AI services on their networks, for example, dedicating a short code or IVR line. In many markets, operators work with governments and NGOs on digital literacy and are keen to add AI services to their portfolios. For instance, MTN and Vodacom in Africa are beginning to integrate AI chatbots for customer service and network optimization, and could do likewise for public goods services. Operators can also subsidize connectivity specifically for these services, e.g., offering free USSD sessions for approved health or education codes, or bundling AI queries and low-cost data plans. This is analogous to telecom-sponsored initiatives like free health hotlines or education portals. Additionally, operators can share location or usage data, anonymized, to help the AI improve without requiring users to transmit raw information. Crucially, regulators and telco associations, like GSMA, can encourage cut-rate SMS USSD fees for social programs, as recommended in industry reports. Governments and NGOs, public and non-profit partners will often steer design and funding. Ministries of Agriculture, Education, or Health understand local needs and can integrate AI tools into national programs, e.g. extension networks, public schools, community health strategies. NGOs, from global ones like UNICEF to local foundations, provide domain expertise, content, and legitimacy. For example, UNICEF has partnered with Viamo to add health content to their system. Similarly, agricultural NGOs and extension services can contribute existing curricula. Donor organizations may fund pilot deployments, as seen with GSMA's Innovation Fund backing agritech in Africa or Asia. Blended finance models, a mix of grants and cost sharing, are often needed early on, since purely commercial rollout may not immediately be profitable. The World Economic Forum highlights that blended partnerships, development agencies, governments, and private firms are essential to reduce investment risk and tailor solutions to local goals. Pricing and affordability. For end users, cost must be kept minimal or free. Several approaches are possible. Tiered micropayments. The Viamo model Nigeria charges users a tiny fee per interaction, e.g. 10 NAN or $0.112. At that price, even the poorest can afford occasional queries, and operators see some revenue to sustain service. Alternatively, services could be free up to a limit, say 5 questions per day, and then pay per use. Subsidies and sponsorship. Public health or education services could be subsidized by health budgets or by development grants, making them free for users. For instance, a government might sponsor free agricultural advice lines to boost productivity. In other cases, services could run ads or sponsor messages from local businesses, though care is needed to avoid biasing advice. Zero rating and bundles. MNOs can zero-rate USSD and SMS for approved AI services, so users incur no cost. They could also bundle data bundles, e.g. an education plan that includes some prepaid content. In some countries, universal service funds, levies on telecoms meant for underserved areas, have been tapped to fund digital education or health initiatives. Policies like these can help keep the user-facing cost near zero. Lowering taxation on devices and SIM cards, as GSMA recommends, also makes these services more affordable in the first place. Local cost sensitivity. Pricing must reflect income levels. Even tiny fees should be scaled. What is small in one country, 10 nan, might be too high in another. Pilots should survey local willingness to pay and adjust via dynamic pricing, e.g., cheaper during planting season, more during harvest.
Ultimately, the goal is access rather than profit.
Many ICT 4D projects have shown that when underserved communities gain free or subsidized information, they often find ways to pay through other means, improved yields, health, etc. The key is that pricing be predictable and transparent, so users can plan. Conclusion: emerging markets are not blank slates. They have mobile networks and some electrification, albeit spotty. But with creative re-engineering, AI can leapfrog these gaps.
The examples above demonstrate that offline-first AI assistance on simple phones
can transform rural life, giving farmers timely agri-advice, informing patients and mothers about health, and supporting remote education. The technical recipe is now within reach. Compact AI models, cheap hardware, solar power, and universal channels like SMS USSD. Success depends strongly on answering local needs. That means designing for local languages, co-creating content with communities, and ensuring trusted oversight. It also means forming partnerships, telecommunication companies to handle networks and pricing, governments and NGOs to curate content and reach people, and community leaders to guide and validate the system. By applying these principles, AI can uplift the 3.2 billion people currently unconnected or underserved in the digital world. Offline AI on low-cost devices can empower smallholder farmers to boost crops, enable villagers to manage health, and help children learn, all within the local ecosystem they know best. In the words of rural innovators, we must meet people where they are, delivering smart tools in the languages, media, and price points that suit them. With thoughtful design and collaboration, AI can finally become an inclusive force for good in the world's most underserved communities. All links to sources are available in the text version of this article. You can find the full article at marketgapideas.com. Thanks for listening. This episode was produced using autopod.co, the platform that turns deep research into podcasts, articles, and SEO content automatically. If you want to create content like this for your brand or business, visit autopod.co and see what automated content marketing can do for you.